Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this second bit of this tutorial series where I'll talk about these particular experiments as stated in the syllabus. I'll continue on the titration experiments, but this time I'll talk about redox titrations. So redox titrations are very popular. In fact, since your O-level or your IGCSE days, you will know that KMnO4 is stated, acidified KMnO4 is stated as a very good oxidizing agent. So H plus KMnO4. This is also stated in the syllabus as something that could oxidize alcohol to carboxylic acid as well. Okay, so this is manganese plus 7. If you could imagine, KMnO4 is a compound with 0 overall oxidation number. Potassium has a +1 oxidation number because it's from group 1. And then you have 4 oxygen, each oxygen of which is -2 oxidation number in a compound. So the manganese there, moving the -8 to the other side is +8. Moving the +1 to the other side is -1. Manganese is +7 because oxidation number must have a sign as well as a value. The +7 is represented by this Roman numeral as stated in the AS Redox syllabus. We use Roman numeral to indicate the oxidation number of this particular species there. You're titrating it with hydrogen peroxide. There is one example, that is the March 2017 paper 3.3. Hydrogen peroxide is H2O2 and the structure looks like H and O. Well, there is a single oxygen-oxygen bond there, characteristic of a hydrogen peroxide structure. So what you have is hydrogen +1. So there are 2 times +1, so there's +2. +2 times oxygen equal to 0 oxidation number for the overall compound. Each oxygen there has a oxidation number of oxygen -1. This is quite special. Oxygen always have a -2 oxidation number in a compound, except in peroxide. Except in peroxide where it's -1, except when it's elemental O2 diatomic molecule when it's 0 oxidation number. Iron 2, the oxidation of iron 2 to iron 3 is very commonly done with acidified KMnO4 in the laboratory. So the color of iron 2 in solution is kind of pale green. Solution, not the one with the hydroxide, but solution, kind of pale green color. Looks almost borderline colorless. So it's going to be dominated by this purple color KMnO4. They will turn pale pink or colorless when, one extra drop of it will not go away. So you stop your titration when you have one extra drop of it, giving you a permanent pale pink. Because if you get colorless still, how do you know this one already fully reacted? You stop when you get a permanent pale pink with one extra drop of these when you're titrating with iron 2. Nitrite ions, I couldn't find an example of this with nitrite ion. It seems like this one is quite unusual. So nitrite ion, as stated in the syllabus, is going to be, I run out of space here, but what you can tell, nitrite, as stated in the syllabus, belongs to NO2 minus. So -1 is the oxidation number of the ion equal to nitrogen 2 times -2. Oxidation number for all the oxygens, of which you have 2 of them, and I add them up with the oxidation number of nitrogen there. So nitrogen is -1 plus 4. Nitrogen is +3 in nitrite ions, and you can be oxidized by oxidizing agent to become nitrogen +5 or nitrogen +4. We are not entirely sure there, but regardless, it will be one of those questions where you can do redox titrations and you will see color changes from purple to colorless or pale pink, but you only stop when one extra drop of it doesn't get reduced anymore, and therefore it will stay permanent pale pink. Ethanedioic acid is a carboxylic acid, but the name itself is dioic acid. That is because ethanedioic acid contains 2 carbons, and both the carbons are carboxylic acid. This is quite unusual and is actually stated in the A2 syllabus, but titration of acid and this thing here, titration of acid and base, was in the previous tutorial, but what we are doing here really is we are not doing acid and base reaction. We are doing a redox titration where we are going to oxidize this ethanedioic acid by totally breaking this carbon-carbon covalent bond, and we'll break the OH covalent bond and we'll get carbon dioxide and water. We'll talk about this in the regards of, by using these particular two examples, the June 2012 paper 3.4 as well as November 2017 paper 3.6. If I don't have time to go through all of these, you are more than welcome to browse through the question paper on your own. These are past year paper questions. They are readily available. I'm just reminding you that they have already existed for a couple of years. It's not really something new, like new, but it's just something that needs to be reminded so that this is from the syllabus and you are looking at the syllabus right now because you know how to use the syllabus as given by the examiners 3 years in advance of your exams. Of course, not just the acid, it's salt which contain its ions. So if I remove the H plus, then I will get the ions like that. And I have another H plus, I'll get the ethanedioic ion. This is an ion, is a dianion. Okay, with a -2 charge. They will also behave similarly and get oxidized by acidified NO4, which will turn from purple to colorless, but you stop in a titration when you get a permanent pale pink with 1 extra drop of it. Thiosulfate and iodine titrations are very, very common because whenever a reaction produces iodines, then we can remove the iodines by using thiosulfate and it will go back from brown to colorless. Although sometimes we use starch indicator to make this blue-black and it will go colorless, blue-black to colorless with 1 extra drop of thiosulfate. Very, very common. I won't talk too much about these, but I will briefly talk about it later on. Actually, I might talk about the thiosulfate and the iodine titration first. So your thiosulfate and your iodines, don't know what's wrong there. Thiosulfate ions is as stated in the paper 3 now. If you look in the paper 3 syllabus, sample paper, that's what I meant. Sample paper for the 2022 syllabus, you will see that in the qualitative analysis table, there is a new addition. It's called S2O32-, and then it will produce a white precipitate. Essentially, it's actually a pale yellow precipitate. It should be a pale yellow precipitate, and that is because when you add acid to it, this is your very, very famous disappearing cross experiment for Redox reactions. You produce a precipitate and the cross underneath the conical flask will disappear, and that is sulfur precipitate that you are forming. These are the insoluble sulfur powder or sulfur solid, which is insoluble in water, and that is formed when thiosulfate reacts with acid. So thiosulfate has this formula which you are expected to know as stated in the new syllabus sample paper 2022, and this was published in 2019, 3 years in advance to inform the students. So S2O32-, the half equation, it will go to S4O62-. Balancing your half equations, you will get 2 multiple of that. Now in balancing the charges, -2 times 2 is -4, -2 times 1 is -2. I need to lose electrons. Oxidation is loss of electrons. I have done loss of electrons on the right hand side there. So the other one is iodine. Iodine gain electrons to give me the iodide. Atoms are balanced, ions are balanced. You will see that 2 electrons on the right, 2 electrons on the left. When you combine the half equation together, you're doing lowest common multiple, primary school mathematics, where the number of electrons have to be cancelled out because, well, you want the oxidation number changes to be balanced out. So since both of them have 2 electrons on either side, I don't need to multiply by anything. I could just add up equation 1 and equation 2 together. The electrons will get cancelled out. This is the overall redox equation, and no electrons appear in it because this is now redox, where I have both reduction and also oxidation. And reduction is your gain of electrons. As you could see, the iodine gained electrons because I've added electrons on the left hand side. So this thing here, this is brown solution. Be very careful. Iodine in solution is brown in color, and iodide is colorless as a solution. But because the brown solution can be quite hard to see towards the end, so what you do is you can add starch, and you use starch in biology to test for iodine, and it will go blue-black when there is starch present, and it will also give you a colorless solution and when there is no more iodine. So you get colorless solutions when all the iodines no longer around or no longer present, and you get that with one extra drop, very, very sharp. So it's quite impossible that you overshoot unless you did not do it drop by drop at the end of the titration there. Okay, of course, one rough and two exact titrations. You will find a lot of examples of this thiosulfate and iodine titration in the past papers from O level, GCSE level, or even AS level chemistry. Very, very common there. But what I'd like to focus really is on the other one involving KMnO4. There's quite a lot of examples there. I've selected a couple of papers, so that's what I'll go through now. So the first one is with H2O2. So this is this is not May, June. This is March 2017, paper 3.3. So this is just KMnO4, the purple colored reagent. Reacting with H2O2, this is your hydrogen peroxide. So this is colorless reagent. And now you get this pale pink color, which is, well, kind of pale pink or colorless, but you don't really stop at colorless because, you know, as this is flowing down from the Buret, I imagine. Fa3 is Buret. Yep, the KMnO4 is in the Buret. So it will keep on turning into colorless because this thing will keep on reducing the MnO4 minus from manganese plus 7. So you must know it as manganese plus 7 in this purple colored KMnO4 species there. And then it will get reduced to Mn2 plus. But the moment this gets into here, you will get the colorless again, which kind of look pale pink colorless. But how do you know it's endpoint? So the endpoint really is when one extra drop of the KMnO4 and it's not going away because there is no more H2O2 to react with it. So one extra drop of KMnO4 from the Buret is not getting reduced. So therefore, it stays as permanent pale pink. So that is how we know it's endpoint. We don't really stop at colorless because how do you know that there is no more H2O2? You only know when the pale pink color is not going away, and this is more noticeable when this thing is present in one drop because the color is very intense, right? So you know, one extra drop of it, it wouldn't be purple. If you stop at purple, you have overshot by a lot. As usual, initial titer, final titer, because you need to do a rough titration. So initial volume from your Buret. Don't forget your tabulation must include the unit. This is rough titration, so make sure you still write down the correct stuff. So this is volume of Fa3. And this is the difference between the final volume and the initial volume. Do not confuse between what is initial and what is final. So initial is at the start. So you probably start from 0.00, but you could have started from 10.00. No worries at all. Make sure whatever you do, all of them must be 2 decimal place, and all of them must be to the nearest 0.5 cm cube, such that your titer was obtained from 2 Buret readings, and each titer has a percentage error of 2 different readings required. So you need to multiply the error in a single reading by 2, and then your titer, which is calculated from the difference of the final minus the initial reading. And then when you are ready for your exact titers, of course, you know, you could have set up with lines and lines in your table. I usually don't, but you know, it's entirely up to you. So you're ready for your exact titers, which you know you could do from 0.00. I don't know the actual value. I don't know, 25.70, let's say. So remember that your rough titrations must always be more than your exact titers because you don't really know where to look for. Okay, if you don't really know where to look for, why would your rough titer be lesser than your exact titer? That's what I don't understand. Some students don't make sense at all. And then you could have started for the next one from, I don't know, 10.50 for instance. And I'm just coming up with random values here. So maybe 25 and let's say 35. Then when I take the difference, final minus initial, I get 25.75. Am I correct? That doesn't look right at all. So how about 36? That looks better because this one will be 5 minus 0, 12 minus 5, 35 minus that. So that is all right. And you can see now your exact titers, maximum difference, maximum error margin there must be plus minus 0.05 cm cube. You're more than welcome to repeat more and more, but if you're a competent chemist, you have done a rough titration, you know roughly where to look for, you would do it drop by drop at the end. Of course, you'll be careful Your goal is to get them to be as exact as possible, but sometimes we are human beings and we cannot get them to be as exact as possible. So, we already done drop-wise at the end of the titration. So as long as they are within plus minus 0.5 cm for my best titers, I should be alright. But everything there must be to 2 decimal place. When you do this on your calculator, when you press 25.70 minus 0.00 on your calculator will show you 25.7. The moment you write 25.7 there without thinking about the accuracy of your Buret readings, that is when you will have made a fatal mistake and you have just thrown away unnecessary marks just like that. Of course, obtain a suitable value is just your averaging. Even though they don't say show clearly how you obtain this value, always show your averaging. And when you do averaging, do not do this on your calculator. Do not ever do this on your calculator, because calculator, even primary school student knows that they do division and multiplication first before doing addition, and your value will be something very strange. It will not be in between your readings, but it will be something that will be way higher than 25.70. So people who are very incompetent in mathematics, you will have problem without the bracket. So bracket, one of the most important thing that you need to learn how to do. And what you get really is, well, if you do this on a calculator, I guess you will get 25.725 on your calculator, and this is no good. If you write this down, again you lose the 1 mark because of the 2 decimal place accuracy. So 2 decimal place for the Buret reading. Your Buret readings, including your averages, must be rounded up to 2 decimal place. You can find all of these, etc, and so on and so forth, really. But they are trying to ask you to find the mole of KMnO4 in this volume of Fa3. So the mole of the MnO4 minus is just C times V. Remember, mole per dm cube must be multiplied by the volume in dm cube. So you had the volume of the KMnO4 in cm cube, so 25.73 there must be multiplied by, well, 10 to the minus 3. Or you can do 25.73 divided by 1000. Unfortunately, if you don't know how to key in times 10 to the minus 3 on your calculator, you are in a bad situation. It's press S, that number, and then exp minus 3 on your calculator. It means divide by 1000. It means times 10 to the minus 3. Concentration of KMnO4 was given earlier in the questions. I'll just do this last bit here. Calculate the number moles of H2O2 in this 25 cm3 Fa1. This is in your titration. This was what you pipette out into your conical flask. So realistically speaking, you're going to compare mole ratio. So if you are very bad at mole ratio, make sure you watch my not experimental, but my theoretical playlist on the use of mole ratio under mole calculations. I personally like to use fractions. So I label the mole of what I want to find, the mole of H2O2. From the equation is 5 mole of H2O2, equal mean equal, top is top, bottom is bottom. And then on the far right, I have just worked out the mole of MnO4 minus from the answer in part 1. And I wanted the mole of H2O2 in the conical flask that reacted with that specific amount from the Buret. So, this answer here really is expressed your answer here. So this is what you want, this is what you want there. I already gotten this answer from the earlier bit, provided I could do the calculation correctly. Now I just need to move up my answer to the top. I do not change anything on this side because this is mathematics. So 5/2 remain as it is because denominator goes up. So this is your answer in part 1. You don't write answer in part 1, of course, because you will have your answer. Let the question guide you step by step, and so on and so forth. Okay, of course, then you will calculate whatever concentration of H2O2. Since you know the volume of H2O2, you want that in mole per dm cube. So change cm cube into dm cube there, and you should be alright. That's it really for that 12 mark question. Okay, what's the next one? The next one will be the usual manganate 7 plus iron 2 salt. So this is the oxidation of iron 2 into iron 3. And what you have really is you're starting it with the mass of the iron 2. So what you get is you have Fe2 plus salt as a solid, and then you want to make it up into solution. So you have a 250 cm3 volumetric flask. This is as stated in the syllabus as one of the instruments that you will need. So what is very important is you have a solution here, but you have a solid here, and you're just adding distilled water to make up stock solutions. Make sure you know the processes. So what are the steps? Describe the steps to make up solution, to make up stock solutions, or they call it standard solutions. So that means a solution of known concentration. You know the concentrations because you're preparing it. The question is, you know here what is the mass of the solid, and you know the MR of the solid. In fact, you don't know the MR of the solid because you want to work out the MR of the solid. Okay, so what I can say is the mole of the solid must be equal to the mole of the solution, because everything in the solid state go into the solution. And guess what? We have mass over MR for the solid. So mass over MR for the solid, and this is equal to C times V for the solution. Only because I draw a simple diagram, you can see everything goes in there. The rest of it is just normal titration. These are to do with the masses, so some mass calculations, and 2 decimal place for the mass reading because it's stated in the syllabus under the list of apparatus. The mass balance that the center need to provide to the students need to be a mass balance that can measure up to 2 decimal places. This is your rough titration, so you always have to perform a rough titration, and then state your rough titer. Make sure your readings are then accurate, and usually it's 2 or 3 titration, which are plus minus 0.10 cm cube for your best titers. Okay, these are your error margin there. Make sure you have the headers, the units, and you'll be marked on accuracy, etc, etc. This is just your averaging. Make sure even your average titer, which are basically from the Buret. So this one has to be to 2 decimal place. Whether whether calculator show you or not, you have to give it to 2 decimal place in the end, etc, etc. The rest of the calculation should be okay. Half equations, so you should be able to write this half equation on your own, as it is also required in A2 as well. This is manganese plus 7. Work out the oxidation number, as part of your syllabus. Oxygen in the compound is -2. This is an ion, so the oxidation number of the ion follows the charge of the ion. That is manganate 7, which is manganese plus 7. The charge of the ion is the oxidation number of the ions, so there's manganese plus 2. This is kind of pale pink or colorless. And you only stop this titration when you get a permanent pale pink, when 1 extra drop of this doesn't go to this anymore. You wanted the oxidation of iron 2 to iron 3. So iron 2 plus going to iron 3 plus. Increase in oxidation number is reduction, and you increase in oxidation number because you needed to lose electrons. And here you needed to lose 1 electron because plus 3 minus 1 give you plus 2, and 1 of each of the iron. You will see plus 5 electrons and plus 1 electrons. This is your reduction. This is your oxidation. So when you want to combine them together, you can see that you need to multiply this whole thing by 5 because you need to cancel the electrons. Primary school lowest common multiple, and hence 1 mole of KMnO4, 1 mole of it reacts with 5 mole of iron 2 plus, 5 mole of iron 2 plus. So the first thing you do really is, this one should be the easy bit, because the mole of iron 2 plus is to the mole of the MnO4 minus. You will see that the mole ratio, because I put down the mole of iron 2 on top, so there will be 5 mole of iron 2. Equal mean equal, so whatever at the bottom equal to 1 mole from the balance equation from the mole ratio given. I think I will have the mole of MnO4 minus because that was the answer in part 1. Calculate the mole of KMnO4 in the titration. So the answer in part 1 is here, and you would just key in the answer which you have, and you want the actual mole of iron 2 plus which you want to find. Of course, then move the denominator to the top. Do not change this side. So do not change this side. That will just be 5 times your answer in 1, because 5 divided by 1 equal to 5 itself. Alright, now what do we know just now? We knew that we started from the solid, so all the solid go into the 250 cm cube solution, but I don't use 250 cm cube for my titration. I only pipette out 25 cm cube for my titration. I use a pipette, so it was 25.0. So here the concentration is the same, but the mole is different. Okay, but here the mole is the same because all the solid goes into the solution. So I'm looking at here now, since the concentration is the same, so here, going to here, the mole will be multiplied by 10 because the volume is 10 times bigger. I could have done in 25.0 cm cube of iron 2 plus. This is the answer in part 3. So here, the mole of iron 2 plus in 25.0 cm cube. Therefore, in 250 cm cube of the iron 2 plus, my factor will be the answer in part 3 multiplied by 250 over 25.0. You will get 10 times bigger answer. Okay, but of course it's not always 250 into 25. Sometimes it's 100 cm cube into 25. So make sure you know how to do the direct proportions. Direct proportion is a lower secondary mathematics. You just need to think about what is the same. N equal to CV, and if the concentration is the same, greater volume means greater number of mole, and so on and so forth. Because the last one, you are looking at this side now. If you have the mole of the solution, this is equal to the mole of the solid, and this is mass over mR equal to whatever your answer in the 250 cm cube overall thing. And you wanted the mR, so move up the mR goes to the other side. This one on top will come down to the bottom, so that is your mass divided by your answer in part 4 then. Okay, so this mass there is from the first part of the question, because you use a mass balance just now to calculate the mass of the solid used after all, etc. and etc. I bet there are a lot of other questions. So what you have here is pipette. Pipette is one single reading. You do not have an initial reading or final reading. You can catch up more of these in my error analysis tutorial videos where I talk about time, volume, temperature, etc. etc. So because you only have one reading, so it's just itself, it doesn't get multiplied by 2, but you're measuring at 25 cm cube, so the maximum percentage error would be like that. It's also known as percentage uncertainty. Uncertainty or error depends on how many reading you need, etc. etc. What is the maximum error in the mass? So it was 2 decimal place mass balance, so it has to be plus minus 0.05. Error in a single reading. Oops, sorry, no, not 0.5, 0.01. Oops, no. Because you'll be reading 0.01 gram, 0.02 gram, because it's a 2 decimal place mass balance. So that means the smallest interval you can see will be 0.01. So the smallest interval you can see is that. Therefore, the error in a single reading must be half of that. That is a single reading. I'm sure you have done this in school as well. So 0.005 multiplied by 2 divided by your actual mass recorded. What was your mass recorded to 2 decimal place times 100%? That is going to be that. What is the maximum percentage error in the mass of, oh actually, I must have done something wrong because that thing there is here. Because this is in the mass of FA1 use. The mass of FA1 use. Because this is just the mass of the beaker, this is just a single reading. So they just want the error in a single reading here. So this is 0.005 gram, like that. And here you have to multiply by 2 because here you have this minus the mass of the empty beaker. So final minus initial, you need the 2 reading there. Okay, so hopefully that was helpful. So I'm going to skip some of these. This one is just, working out the formula of this water crystallization by doing titration with this iron 2 plus, because the NH4 plus being a double salt, the NH4 plus does not react. It does not get oxidized by the H plus KMnO4, but this one can get oxidized. So in this mixture of double salt, so only the iron 2 plus get oxidized, and you should be able to work out the MR and take away the MR and then divide the difference by 18 to work out how many X do you have there. So this is for the summer 2015, June 2015, question paper 3.5. You can play around with that. I think the next bit really is I want to focus on this ethanedioic acid. Ethanedioic is ion, so it comes from ethanedioic acid. After the acid donates the protons, after the acid loses the H plus, then it's no longer acid. This is the salt. This is the anion, whereas this is the dioic acid. It's called ethanedioic because 2 times carbon. So now, what is so special about this titration? It's very special because, okay, you need to heat. You need to heat it, and there's the problem here. You need to heat it. Where's the heating? Where's the heating? Yeah. I guess this is the one that doesn't require heating. Why is this one not requiring heating? Maybe because this is the salt. I think this is the salt that doesn't require heating, perhaps. But the other one definitely require heating. Let me show the other one first. This one is, yeah, this one definitely require heating, you see. Place the conical flask and heat it until it's approximately 70 degrees Celsius, so that this one is a faster reaction. But it's quite unusual that you have to heat your conical flask, you know, with the solution that you prepared out before you actually do the titration. It's quite unusual, okay? That's why I said this is quite a special one to think about. This is MnO4 minus, this is 5 of that. This is very slow on its own. Why is it very slow on its own? Because it's got high activation energy. That's why the reaction is slow. Why does it have high activation energy? Look at the -1 charge and the -1 charge. Yeah, A2 level question, the negative charge will repel each other. Negative charges will repel each other. They have to collide. Collision frequency says your reacting particle have to collide. This will be unfavorable because they will repel each other. So high activation energy there, very slow reaction. But of course you can overcome activation energy by doing high temperature. So what we are doing is we are applying high temperature to make it react at a better rate, something that you can see with the color changes from purple to a permanent pale pink color. You see, you stop only when you reach a permanent pale pink color. One extra drop of that acidified KMNO form will not go away. It will not react with this anymore because no more of this is present. That is your endpoint there. Apart from that, everything else is pretty much the same. Of course, when you do your calculations, this is your CO2 minus like that, and 2 of them, and it's to the mole of your MnO4 minus. From the balance equation, you have 5 mole of these and 2 moles of that. So, you know, whatever, C times V, but the mole ratio there. Okay, so mole ratio is just based on the balance equations. These are equal again. These are mole, actual mole of this, actual mole of that from your titration itself. I would say the rest of the titration is pretty much the same. It's just this bit that requires heating because of the slow reaction, high activation energy. This is in winter 2017. So October 2017, November 2017, paper 3.6. So not very long way from now. This one, they don't ask you to heat it, which is quite surprising. Maybe this one is somehow it's fast on its own. I'm not entirely sure. Anyway, so just following the instructions, they don't say heating, but this is again between this sodium ethanedioic as well as KMNO4. So it's a similar kind of chemistry. And this is also quite a recent paper. Well, not recent, like 10 years ago. At the moment I'm making this video. So this is June 2012. Paper 3.4. So it's not like it hasn't come up before. It is something that is in the syllabus. I've just completed almost everything except for the nitrite. I couldn't find a question on that. So, you know, they could potentially ask you that next time. But it will have similar kind of concept. You do the titration with this purple colored KMNO4, manganese plus 7, until you reach a permanent pale pink color with 1 extra drop of these because none of the nitrite is present anymore. The ethanedioic acid usually require heating, so quite a special one. Iron 2 is quite a normally asked thing. With hydrogen peroxide also not too bad. Thiosulfate and iodine is a common redox titration. Sometimes you use starch, sometimes you don't, but it's just a normal redox titration. Very, very common kind of thing. Hopefully that was useful. That's it really for this tutorial video. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. I'll see you in the next tutorial video where I'll continue on rates, gravimetric, thermometric, as well as gas volume experiments.